Some examples of how to evaluate rational exponents. The directions here are simply to evaluate. You should not be using a calculator for this. According to the definition of b to the 1 over n, in this case 81 to the 1/2, this is equivalent to the square root of 81. That means what number times itself is 81? That number is 9. Second example, 27 to the negative 2/3. The order in which you do these problems does not matter. So the way that I'm going to do this may be a different order than what you would have done, but if you follow the rules and get the same result, then that's all that really matters. I don't like the fact that my exponent is negative. So to change it, I'm going to take the base and reciprocate it. My base is 27. Reciprocating it would be like so. My exponent for that 27 is 2/3. Next, I'm going to use a definition of rational exponents, which means I can take this 27 to the 2/3 and rewrite it so it's the cubed root of 27, and then that is squared. Someone else might have chosen to square 27 and then cube root it. Here's why I wouldn't do that. First of all, what's 27 squared? You hear that silence? Yeah, that's an awkward silence because I don't know what it is either. We don't want to use a calculator unless we have to, so let's not. What's the cubed root of 27? Well, let's say you're sitting there thinking, how could I possibly know what the cubed root of 27 is? Well, let's try to figure it out. Let's start with the smallest possible solution, which would be 1. Does 1 times 1 times 1 equal 27? Of course it doesn't. How about 2 times 2, which is 4 times 2? Is that 27? Nope. That's 8. Let's try 3. 3 times 3 is 9, times 3 is 27. Therefore, the cubed root of 27 is simply 3. So this becomes 1 over 3 squared. 3 comes from, once again, the cubed root of 27. What is 3 squared? Well, that is a 9er. 9er is trucker talk for 9. So that would be 1/9. Example 3. 7 to the 1/4 times 7 to the 7/4. This would be the product property. When you're multiplying two things that have the same base, 7 is our base, simply take the exponents and you add them together. Our exponents are fractions, and they have common denominators, so you just add the numerators. 7 plus 1 is 8. Denominator stays the same. 8 divided by 4 is 2, so this reduces. What is 7 squared? That means 7 times 7, which is 49. Number 4. Cubed root of 125. What number times itself again is 125? Let's say you don't know the answer. It's easy to try to figure out. Let's say that you think it might be 2 times 2 times 2. Well, that's 8. That doesn't work. How about 3 times 3 times 3? That's 3 times 3 is 9, times 3 is 27. Doesn't work. 4 times 4 is 16, times 4, 64. I know that because Super Nintendo was 16-bit. Nintendo 64 was supposed to be 4 times as powerful. So 16 times 4 is 64. 5 times 5 is 25. If you have 5 quarters, you have 125 cents. So the cubed root of 125 is 5. Example 5. cubed root of 343 to the negative 2. Once again, there's lots of different orders you can do this in. I'm going to go inside the parentheses here. We have the cubed root of 343. What is that cubed root? We know it's not 5, because 5 times 5 times 5, we just found out it's 125. Let's try 6. 6 times 6 is 36. Times 6 more. I'm not sure. 6 times 36. 6 times 6 is 36. 6 times 3 is 18. 19, 20, 21. That didn't work. That's 216. Let's try 7. 7 times 7 is 49. 49 times 7. Carry it as 6. 3 times 4 is 28. Plus 6 will be 34. Looks like that works. So erase this, get it out of my way. 7 times 7 times 7 is 343. Therefore, the cubed root, 343, is 7. So this now is 7 to the negative 2. I don't like the negative exponent. I mean, who would? To change it, reciprocate 7, 1/7, and the exponent then changes sign, so now it's positive. 7 squared is 49. So this is 1/49. One more example, with the directions being just to evaluate. 49 to the 5/4 divided by 49 to the 3/4. Once again, lots of different orders you could do this in. I'm going to choose to use the quotient property first, which says if you take a base that's divided by the same base, in this case our bases are 49, you can take the numerator's exponent and subtract from it the denominator's exponent. 5/4 minus 3/4 would be 1/4. Pardon me. 5 minus 2. 5 minus 3 is 2, not 1. 2/4. And then 2/4 reduces to 1/2. 49 to the 1/2 is saying the same thing as square root of 49. Square root of 49 is 7. Next set of directions, express using rational exponents. Express this using rational exponents. So you have to use rational numbers. Numbers that you could write as a fraction using integers is what a rational number is. So this right here is saying the 4th root of x, but it's really saying the 4th root of x to the 1st. Take your base, which is x, your previous exponent, which was a 1, in your exponent, and the root, the 4th root, is the denominator in your exponent. So it becomes x to the 1/4. Number 2, we got the square root of xy cubed. That would be x to the 1/2 times y to the 3/2. Once again, the exponents become the numerators in your exponent, and the root becomes the denominator in your exponent. Number 3, we have the cubed root of 8x cubed y to the 6th. This would be 8 to the 1/3 times x to the 3/3 times y to the 6/3. 8 to the 1/3, or the cubed root of 8. 2 times 2 times 2 is 8. So that just becomes 2. 3/3 reduces to 1. 6/3 reduces to 2. So this is going to be 2 times x times y squared. Example 4, using rational exponents, we could write this as x to the 6 halves times y to the 3 halves. 6 halves reduces to 3. So that is our rational exponent form. Number 5, we have the cubed root of 64 x to the 9th y to the 15th. So that would be 64 to the 1/3, which means the cubed root of 64, which we found out earlier was 4. 4 times 4 times 4 is 64. And then x to the 9/3, that reduces to 3. And then y to the 15/3, which reduces to 5. So we get 4x cubed y to the 5th. Number 6, we have the 5th root of 15 x cubed y to the 15th. That's going to be 15 to the 1/5 times x to the 3/5 times y to the 15/5. This last fraction reduces, none of the other ones do. So we get 15 to the 1/5, x to the 3/5, and y cubed. This next set of problems, the directions are to express using radicals. So 15 to the 1/5. 15 goes inside the radical symbol. Since the denominator of the exponent was a 5, that's the root. And then the exponent of 1 is 15 to the 1st, which you don't need to write that. So it's the 5th root of 15. Number 2, x to the 3/4 times y to the 1/4. Our denominators there are 4, so that's the 4th root. And then it's our bases, and then the exponents are the numerators of the previous. And once again, I don't need to write that first for the y. So the 4th root of x cubed times y. This next one is a little more complicated. First of all, the whole number 15 doesn't have an exponent, so we're going to leave that outside of the radical regardless. The next thing you'll notice is the exponents, the fractions that are exponents have different denominators. Those need to be the same so we can put it under one radical. The least common denominator between 3 and 5 is 15. So we're going to multiply the 1/3 top and bottom times 5, which is going to give us 5/15, and the 1/5 top and bottom by 3/15. Now we can write this as 15 times the 15th root of x to the 5th y cubed. You need those common denominators so you can write it under one radical. The next set of problems was to simplify. This first example, we have a power to a power in the x to the -2 to the 4th, which you can write as x to the -2 times 4. -2 times 4 is -8. Now we can use the product rule. Multiplying two things, x and x, same base, you can add the exponents. 8 plus 8 is 0. X to the 0, of course, is 1. Why the long face, guy? See that there? See the long face? Not happy, he's not really sad, he's just there. No? Sorry. Number 2, multiplying these. Since they both have the same radical, they're both square root, we can put them all under the same radical. And the same bases, we can add the exponents. That's the product rule. 3 plus 4 is 7. 2 plus 5 is also 7. Now this reduces because the 7th, it's the square root of the 7. Well, there's a couple different ways to write this, and the directions don't really say how to write it. You could just simply stop at changing this to x to the 7 halves times y to the 7 halves. That's an exponential form. If you want to leave it in radical form, you can reduce it because x to the 7th, you could say, I don't want to get too crazy here, but I'm probably going to get a little crazy. You got 7 of those x's. 1, 2, 3, 4, 5, 6, 7. Of course, you have 7 y's as well. Each pair, you could take one number to the outside, because what times itself gives you x times x? Well, it's x, so you can pull one out to the outside. Each of these groups, you can pull an x out to the outside. Same thing with the y's. So this reduces to x cubed, we pulled 3 to the outside, times y cubed, we pulled 3 to the outside. We have an x and y left on the inside. So here's a different way to write this. These are two different versions of the same answer, both acceptable. This next one, we have the power of a product here twice. So 5 times a times c to the 1/3, we could just say 5 to the 1/3 times a to the 1/3 times c to the 1/3. And this next one, a squared times c cubed to the 1/3, we could say a to the 2 times the 3rd, and then c to the 3 times the 3rd. Simplifying this a bit, 5 to the 1/3, a to the 1/3, c to the 1/3, and then a to the 2 times the 3rd would be a to the 2/3, and then c to the 3 times the 3rd. Could write it as 1, I'm going to write it as 3/3, and you'll see why here shortly. I don't want to reduce that yet, because I have the same bases here that I'm multiplying. And to do that, I want common denominators. So 5 to the 1/3 stays. I have an exponent of 1/3 and a 2/3, so I can add those together. 1/3 and 2/3 is 3/3, which is 1. And then c, my exponents are 1/3 and 3/3. 1/3 and 3/3 is 4/3. So here is a version of that answer. Last problem. Red blood cells are circular-shaped cells that carry oxygen through your bloodstream. The diameter of a red blood cell is about 7.75 times 10 to the negative 7 meters. Find the area of one of these cells. Express your answer in scientific notation. Area of a circle is pi r squared. R being the radius. If the diameter is 7.75 times 10 to the negative 7, then the radius is half of that. Half of 7.75 is 3.875 times 10 to the negative 7. So that means this is pi times 3.875 times 10 to the negative 7 squared. Simplifying this a bit, the squared we can apply to the 3.875. We can also apply it to the 10 to the negative 7. The power to a power property says that we would multiply those exponents. And I'm going to use a calculator for this. 3.875 squared times pi is approximately 47 point, let's say, 173. We're supposed to express this, I should have written here that our radius was m meters. When you square meters, you get square meters. So we're at square meters here. We're supposed to express this in scientific notation. Is this in scientific notation? It is not. 47 is bigger than 10. So we have to change it. Put the decimal place one place to the left. It's 4.7173 times 10 to the something m squared. 10 to the what? Is it going to be negative 13 or is it going to be negative 15? Let's try to reason through what this is going to be. Hopefully you would agree that 47.173 is equivalent to 4.7173 times 10. Multiplying it by 10 is going to make it 47. That's 10 to the first. So in essence, when you get to this part right here, I could have written that as 4.7173 times 10 to the first times 10 to the negative 14. When you multiply same base, 10 and 10, it's a Chinese person that's happy. When you multiply 10 times 10, you add the exponents. 1 plus a negative 14 is negative 13. So that is the approximate area of this red blood cell.